All right, we're back with electron transfer reactions. And in this portion of the chapter, we need to use oxidation numbers. So we'll get some more practice if you didn't have enough, but we'll get plenty in lab and homework as well. We need to know who's giving and who's taking. And specifically, we're talking about electrons because this is the flow of electrons called electricity in the end that we're after. It's important to know that you can't have one without the other. So you can't have a loss of electrons ever if there's not somebody to gain them. So there is no such thing as an oxidation reaction. There is no such thing as a reduction reaction. You have to have redox, so reduction and oxidation at the same time, in order for a chemical reaction to take place. So in the homework you'll see a few of those where it looks like there's a couple right answers, but again, there is no oxidation reaction, period. There is no reduction reaction, period. There's only both at the same time. So you can't have electrons, falling off an atom if another atom is not ready to receive them. So be aware that it's a two-way street. So in this idea of electron transfer, we need to figure out who's the giver and who's the taker. An easy way to understand this idea is think about valence electrons and how valence electrons can change in order to be typically like noble gases. We saw previously that that's not always the case. Sometimes you're going to get bullied and not get exactly what you want, and that happens. A fun way to remember this is Leo, the lion, says GER. So this Leo-GER process is the easiest way to remember the definitions we're going to use for a majority of our homework. If you think of Leo, L stands for loss, E stands for electrons, O stands for oxidation. So losing electrons is oxidation of your atom. Gaining electrons is reduction. So reduction is going to make you negative, oxidation is going to make you positive. That's the idea. So notice up here, as we go from this atom A over to its cation, notice in this situation, A is losing electrons and it becomes positive. That would be a Leo. Loss of electrons is oxidation. Notice here B is gaining the electrons from A. Gaining electrons is reduction, and that makes you negative. Oftentimes biology uses a very similar definition. A lot of biologists on campus actually use oil rig, which is the exact same idea. The reason I don't like oil rig is because it doesn't remind you of the most important feature of this process, and that's what are you losing? It's great to be losing, something or gaining something, especially if it's gaining money. But what are we talking about? So I like Leo-GER better because it mentions exactly what we're losing, and that's electrons. If you remember that electrons are negative, when you lose negative, your positive protons are still there. So when you lose electrons through oxidation, you're going to become more positive. And when you gain electrons, because they're negative and you have a fixed amount of protons that are positive, you're going to become more negative. So it really just depends on the example, on what we're looking for, but it is a Leo versus GER kind of issue. And if you can figure out who's the Leo, you might be able to get the GER by default if there's only two atoms. So as we look at lots of different types of reactions that we've seen back as early as week 10, we've seen these really throughout the entire semester. We just haven't really identified much of what's going on. Notice here with sodium we have no charge. Chlorine we have no charge. But as sodium goes to Na plus 1, that's a loss of electrons. That's a Leo. And as chlorine gains those electrons and becomes -1, it's going to be reduced because it's gaining electrons. That's GER. So gain of electrons is reduced, loss of electrons is oxidized. So over here, sodium is the Leo and chlorine is the GER. You can imagine that in a marriage reaction, divorces will be the opposite. So instead of giving and taking electrons, you're basically giving and taking them back. And that's what we see down here. You can imagine that the oxidation states that we just talked about would be a -2 and a +2, no different than what we've seen in exam 2. But if you're a +2 and then you go back to a 0, you've accepted those electrons back that you gave oxygen a long time ago. Oxygen's a -2, it goes back to 0. It had to get rid of those -2 electrons, -1 each, but -2 total electrons. And in order for that to happen, those oxygen ions were oxidized because they were losing those negative charges back to mercury, those electrons back to mercury. Mercury was reduced because it gained the electrons that oxygen had once given it. The only reason this happens is because there's a lot of heat. There's a lot of motivation to give those ions that are in their noble gas state back. So if you're oxidized, that's a loss of electrons, that's a Leo. And then mercury here is the GER. So you have to have both. You can't have one, you can't have the other. You have to have both. You have to have a loser and a gainer in electrochem. So as we look at single replacement reactions, we see something very similar. We see calcium with no charge. But eventually we see calcium with a +2 charge. In order to become a +2, we had to lose electrons, and lose is for Leo, right? L for lost, O for oxidized, so here we have our Leo. But notice in this situation we have 2 left. We have hydrogen, which was a +1. It became a 0. So if it went from a +1 to a 0, it had to gain a -1, and that's reduced, so that's your GER. And then notice uniquely here what happened is chloride was a -1 before and a -1 after. You could reverse cross these charges to see that. But if you're a -1 before and after, that's what we call a spectator ion. And those are present in single replacement reactions as well. In that married couple, somebody has to stay the same, and in this case, chlorine did. As you look at a combustion reaction, very similar. You can imagine if this is a +4, because there's 4 +1s total, this is going to be a -4. Oxygen's elementally 0. That was rule number 1. Elements are always 0 by themselves. And if we look over here, we can see that they've changed a little bit. Here we have 2 -2s. That's going to be a -4. Here we have a +4 to make up for it. Hydrogen's still a +1, so that's a +2 total. It's a +1 each atom, so +2 total. Oxygen is a -2. So oxygen was a -2 there. It was 2 -2s here, just like it was 2 +1s there, and just like it was 4 +1s over here. So when you look at that, who didn't change? Hydrogen was a +1 over here, and hydrogen was a +1 over here. It doesn't matter how many atoms you have at a time. The simple fact that hydrogen was a +1 before and after tells you spectator ion. So even in combustion reactions, there's spectator ions. But what we do see is carbon was a -4, and now it became a +4. That's a tremendous amount of electrons being transferred. Because you're a -4, you have to lose 4 electrons just to get to 0, and then you have to lose 4 more in order to get to +4. So we lost 8 total electrons. That's a huge oxidation process. This is why blowing things up is so dangerous. There's a tremendous amount of electron transfer going on, especially if you think about molecules like octane, where we have a lot more carbons getting a lot more oxidized. Oxygen went from 0 to -2 in both situations. So because oxygen was gaining electrons, it was reduced. So gain is GER, and over here for oxygen, loss, oxidation, that's a Leo, and that's a great first step in order to understand these kinds of reactions. One of the biggest things to think about in this chapter to make it a little bit easier, because nobody really likes math, is notice we never chose products. Products will be answers because they're going to have an A, a B, a C, a D in the homework. Just remember that products are never answers. We just use them to better understand the process of electron transfer. Always choose reactants. Products were only answers for spectator ions and precipitates, and that was week 10. In this chapter, it's going to be reactants. They're going to be answers because those are the losers and the gainers. Our other type of reaction was a major focus for week 10 and week 11, and now we know why. As you look at these reactions, nobody changes. So silver was a +1, it's still a +1. Nitrate was a -1, it's still a -1. That means nitrogen was a +5 both times, oxygen was a -2 both times. Nobody changed. Sodium is a +1, still a +1. Chloride's a -1, still a -1. Notice we have all spectators. That's not always true, but it looks like it on paper. Sometimes when you have two ions that could be spectators, but when they stick together and make a solid, then we get a precipitate, and that's different. So that's still an issue, but just not an issue for this chapter. With regards to losers and gainers, nobody lost, nobody gained. There is no oxidation, there is no reduction, there is no redox in these kinds of equations. Acid-base reactions we just saw, we have a +1 and a +1 twice. We have a -1 and we still have a -1. We have a +1 metal, we still have a +1 metal. Oxygen still a -2, hydrogen still a +1, just like they are over here. Nobody changes. Sure, it's true and important that this is a liquid and that's just like a precipitate. But for purposes of electron transfer, double replacement never ever does it. So when you see double replacement, you immediately know to stay away from it. It's not electron transfer. There's no LEOs, there's no GERs, there's no nothing. They're just trading partners looking for color changes or production of water and heat. So as we start looking at examples, we need to know who's the loser, who's the gainer. And we can use oxidation states to be able to figure that out. So you can imagine in this situation here, we could do exactly what we did earlier where we say carbon plus 4 hydrogens equals 0. Carbon plus 4 positive 1s equals 0. If we have 4 positive 1s, then we need to subtract 4 on both sides. Subtracting 4 cancels +4, -4. Carbon equals -4, just like we said it would. And that's what we see up here. So notice the process of finding oxidation states comes in handy because sometimes we need to know the charge of one of the atoms in a bigger, larger molecule. You can imagine the same thing over here. Carbon plus 2 oxygens equals 0. Carbon plus 2 -2s by rule equals 0. In order to get rid of a -4, we're going to need a +4. Those will cancel. What you do to one side, do to the other side. You get carbon equals a +4. And notice that's exactly what we need in order to get +4. So sometimes we have to do oxidation state calculations and LEO-GER processes at the same time. Once you realize that from going from -4 to +4 is a loss, in this case, of 8 electrons, that's LEO. And then you can very quickly realize that you either have hydrogen or oxygen that has to accept, that has to gain those electrons. Once you realize that hydrogen's in a compound before and after, it's a +1 by rule before and after. That's enough to realize that it didn't change at all, and that oxygen did instead. One of the confusing parts about this chapter is these definitions. So oxidizing agent is the exact same thing as somebody being reduced. So the easiest way to think about it is, in order to oxidize something else, I have to be reduced. So a fun way to memorize this idea is that they are opposites. They're kind of like double agents. If you're gaining and oxidizing that process back and forth, notice that carbon is being oxidized. If it's being oxidized, it's being the LEO, right? Oxygen is being reduced. That's being the GER, R for reduced, O for oxidized. But in order to be reduced, you're forced to oxidize something else. So it's like a spy movie where you have a double agent. It's working for the side of reduction because that's what it wants, but it's forcing other people to, reveal their secrets, to be oxidized as a result. So because oxygen is being reduced, it's forcing carbon to be oxidized. So you can imagine the opposite is also true. If you were to think of the reducing agent, you would think of carbon, because if carbon's giving up electrons, it's going to force somebody else to take them. So in this situation of that double agent, you're kind of paying off, oxygen with electrons to get information. So the best kind of clue or help that I can give you here is if you see the word agent, think opposite. Because if you're oxidized, you're going to be the reducing agent. If you're reduced, you're going to be the reducing agent. But students that like to put reduced and reducing agent together are going to get half of those questions wrong. If you think oxidized and oxidizing agent are the same thing, you're going to get half those questions wrong too. So as soon as you see the word agent in the homework, think opposite. So reducing agent equals oxidized, oxidizing agent equals the reduced atom, and it won't be as bad as it could be. So let's try an example. What we're going to show you is what's called a half reaction. Half reactions are when you show before and after what's going on. In this case, there's only two atoms. So there's a before and after for each one. So all we did is take in the only atoms that exist, list them, and then do separate half reactions of each one to see kind of who's the loser, who's the gainer. First thing we should notice is phosphorus is in the elemental form, it's sharing with itself. Bromine is in the elemental form, it's sharing with itself. So if they have no charge, that makes our lives a little bit easier. You can imagine that if we wanted to balance this, we could. It doesn't really change the answer, so I'm going to avoid that for now, but at the end I can show you that, again, it doesn't matter. Over here, though, we have an issue because now these guys are kind of married. They're together. This is a combination reaction. The electronegativity of phosphorus is 2.1. For bromine, it's 2.8. That means bromine's going to get what it wants. Traditionally, we would think phosphorus is a -3, but it's not. Not when it has 3 bullies attached to it. So you can imagine that if we do phosphorus plus 3 bromines equals neutral compound 0, we're going to get phosphorus plus 3 -1s equals 0. We're going to add 3 to both sides in order to get this 3 to go away with a -3. Phosphorus equals a +3 for the first time of the semester. That should make sense. If this is a +3, it's going to balance with 3 -1s, which is a -3. So you can always check your work, which is nice. That tells us, though, that phosphorus went to a +3, not what it wanted, but it's what it got. And bromine went to a -1, which is exactly what it wanted because it's the more electronegative bully. Now the trick is how. How did you go to a +3? How did you go to a -3? Well, sometimes students are not good at this because it's chemistry, and chemistry is scary and tough, and so on and so forth. You can imagine, though, just try. If you put a negative on both reactions as reactants, only one is going to work. Does it make more sense that negative plus 0 equals +3, or does it make more sense to think that negative plus 0 equals negative? Well, hopefully the top one looks, ridiculous, and that's the case. You can't have negative and 0 and ever make positive ever. That tells us that the electrons have to go as products in this half reaction over here. Specifically, 3 of them, 3 negative and 3 positive, make 0. Just like -1 and 0 make -1. That's enough to say that who's the loser? This is a loss of electrons. This is a gain of electrons. We don't want to use products, we want to use reactants. So if you're a loser of electrons, you're a Leo. So that means you're oxidized and the reducing agent. If you're gaining electrons, you're being reduced, and that's going to make you the oxidizing agent. Real quick, I'll show you that if we were to balance this reaction, this would now be a 4. This would now be a 4. This would be a 2. This would be a 2. If we have 4 positive 3s, that's going to be now 12 electrons. If we have 2 negative 1s, that's going to be 2 electrons in. And what's important about this feature then is if we're pumping out, if we're losing 12, we should be gaining 12. And that's exactly where this 6 comes into play. If this process were to happen 6 times, and it has to, then we can get 12 electrons in. So balancing the equation is showing us that there's a reason we have to balance it, because there's an electron transfer that has to be complete. You have to have just as many electrons lost as gained. There is no free electrons left over. You either go to completion or you don't go at all. And that's how chemical reactions work. But notice, did this change who is oxidized and who is reduced? No. Does it change who is reduced in the oxidizing agent? No. So you don't have to balance half reactions in Introchem to figure out who's the Leo, who's the GER. In this case, we had phosphorus being the Leo. It's the one that became more positive. And we had bromine being the GER. It's the one that became more negative. So getting practicing this, understanding this is a majority of this chapter, because sometimes you have to use oxidation states in order to figure out who's the loser, who's the gainer. The remainder of this chapter is all about batteries, so we'll come back in an additional video and show you that.